We're back at AP Review. This is 2016 AB Free Response 6. We're given this really big table of values for f, f prime, g, and g prime at the x values 1, 2, 3, and 6. So the functions f and g have continuous second derivatives. The table above gives values of the functions and their derivatives at selected values of x. So when you see a problem like this, before you even walk into it, what's likely to happen is you're going to be asked to apply your knowledge of things like the chain rule, the product rule, the quotient rule, with functions where you can't see the functions and you're only given certain values of them. So this is a really good way for the AP to sort of think outside the box and test those rules. And it used to be a pretty common AP multiple choice, and now it's a pretty common AP free response. So cool. Part A, let k of x equal f of g of x. Okay, so k of x is a composition of functions, right? So this is a chain rule, f of g of x, right? Write an equation for the tangent line to the graph of k at x equals 3. Okay, so if we want a tangent line, right, anytime we want the equation of a line, we're going to need two things. Okay, number one, we're going to need a point, right? So that point is going to be 3, comma, whatever k of 3 is. So we're going to have to use the table to find k of 3. And the second thing we're going to need is a slope. Well, the tangent slope to k at x equals 3 would be k prime of 3, right? And that prime kind of got swallowed up by the p in slope, but you get the idea. So k prime of 3. So those are the two things we're going to have to do. I'm going to start with the point because technically that's an Algebra 1 skill. So when I go to start by finding the point, right, k of 3 is going to be f of g of 3, right? So what I want to do first is find g of 3. I look at the table and I say, okay, here's where x is 3, here's the g value, g of 3 is a 6. So that means f of 6. Then I go to the f column and I say, okay, what is f of 6? Well, f of 6 is a 4. Cool. So I now have my first point, right? Like I have, or my first piece of information, right? My point is 3, comma 4, right? X, comma y. Great. Second thing I need is k prime evaluated at 3. So k prime of x, right? So this is now the slope, right? K prime of x is going to be the derivative of the outside, so f prime of g of x, I didn't change the g of x at all, times the derivative of the inside, which is going to be g prime of x. So that means that k prime of 3 should be f prime of g of 3 times g prime of 3, right? Well, we already found g of 3. G of 3 was a 6, right? We already did g of 3 is a 6. So that's f prime of 6 times g prime of 3. So now I just have to find those two values on my table. So f prime at 6 is a 5, right? And g prime at 3 is a 2, so I get a 10. So now I have a slope that's 10, right? And I have a point that's 3, comma 4. So my answer then, right, which I think should be, yeah, you should be able to see that. So my answer is going to be y minus the y value, which is the 4, equals my slope m, x minus the x value. Now that answer is technically fine because they didn't say solve for y, but the safest bet to keep the AP happy is to just add this 4 over separately, and you're going to get y equals 10, the quantity x minus 3 plus a 4. Right? That's usually the safest way. You didn't simplify much, you just added the 4 over, and that's it. But you should be fine with this first answer because they didn't expressly say solve for y. All right, so after that, we don't use the k of x function anymore. Congratulations, that's it, no more k. On to the next function, part B. I'm going to try really hard not to erase this table so I don't have to recreate it. Part B, let h of x be defined as g of x divided by f of x. Find h prime of 1. All right, cool. So this is a quotient rule, right? So h of x is g of x over f of x, right? So I have a low function and I have a high function, right? So when you do a quotient rule, the derivative of a quotient is low d high, so that would be, so f of x times g prime of x, minus high, which is g of x, d low, which is f prime of x, draw the line, square the low, so f of x quantity squared, right? So now h prime of 1 is going to be f of 1, g prime of 1 minus g of 1 f prime of 1 over f of 1 quantity squared. And really this just comes down to being meticulous and not accidentally plugging in the wrong values, right? So f of 1 is a negative 6. G prime of 1 is an 8, right? Minus g of 1, I go to g, I go to 1, is a 2, right? And f prime of 1 is a 3, right? All divided by my f of 1, which I already found to be a negative 6 quantity squared, right? So now I just clean stuff up, right? So I end up getting that h prime of 1 is so this is a negative 48, right? Minus a 6. So that's a negative 54 on top of a positive 36, right? And I can go ahead and cancel 18s out of that, and I get negative 3 halves, or negative 1.5, whichever one you like better. Arguably, you could leave it as negative 54/36. The AP is not usually hugely, you wouldn't leave it here, right? You're expected to go past this spot where you have a really rough quotient rule. But if you left it as negative 54/36, they'd probably be fine with it. Lastly, part C. So, part C doesn't involve, I just lost some of that, but we're going to hope that it's okay. Hang on. This was a 6. I'm pretty sure that was a 4, and I think that's all we lost. Okay, part C. Part C, you don't need K or H at all. So you're integrating from 1 to 3 of f double prime of 2x dx, right? Okay, so when you integrate f double prime, you're going to get f prime, right? But the problem is that this is technically a u sub problem, right? Like, you have a function in your function, right? This is technically u sub. And if you don't need to do the u sub, that's fine. If you can just say in your head, oh, if my u were a 2x, my du would be a 2 dx. So what's basically going to happen is you're going to end up with a 1/2 in front of this. Like, if you think about it, if you derived this expression, every time you derive it, or differentiate it if you want to be more specific, every time you differentiate this expression, you'd have to times by 2 because of the chain rule. So if you were to integrate this expression, you'd have to times by 1/2, essentially undoing that chain rule. So this is going to end up being what happens when you integrate f double prime, which is f prime, but times the 1/2 because of that chain from 1 to 3, right? So when you plug this in, you're going to get, this is a 1/2 f prime of 6 minus that 1/2 f prime of 2, and then you're just going to plug in those values, right? So that's going to be a 1/2 f prime of 6 is a 5, minus a 1/2 f prime of 2 is a negative 2, right? So you're going to get 5 halves plus 2 halves, which is totally 7 halves, and that's your answer.